In this video, I'll be talking about what is Ferrers diagram, and this Ferrers diagrams we use for representing a partition of an integer. So before I discuss the Ferrers diagram in detail, let me to start with the definition of the partition of an integer. A partition of a positive integer n is the representation of n in terms of the positive integers n1, n2 up till nr such that whose sum is n. And these parts are written in non-increasing orders and we call these ni's as parts. So for example, if I take n is equal to 4 and I want to write all the partitions for 4, we can see 4 itself is a partition, 3 plus 1 it's a partition, 2 plus 2 is a partition, 2 plus 1 is a partition, and then 1 repeating 4 times is a partition. So we also represent that Pn, this is the total number of partition for that particular integer, and in this case if P4 we want to write, there are 5 partitions. So we can say this represent number of partitions of n, and n is of course here we have considered as the positive integer n. Now we want to understand what is the Ferrers diagram corresponding to this partition, or is there any graphical representation to represent any of the partition that I've listed here. So the Ferrers diagram, which is due to Norman F. Ferrers and hence called as Ferrers diagram, for a partition n equal to n1 plus n2 plus nk of a positive integer n, where parts are written in a non-increasing order. This is an array of dots or cells. So when we say it as cells, this is also known as Young's diagram. So we can write it down, Young's diagram. So when we use the notation in terms of the cells, we call this as a Young's diagram. Otherwise, we may conveniently call this as a Ferrers diagram. This is an array of dots or cells, left justified dots with ni dots in the ith row. And for each partition, we can represent a Ferrers diagram. So now to understand this Ferrers diagram, let me to take the same example for which I have written the partitions. So we consider n is equal to 4 and there are 5 relevant partitions corresponding to 4. So I have named these partition pi1, that is 4. This is one of the relevant partition. Then I have named another partition pi2. This is 3 plus 1. I have named another partition pi3, 2 plus 2. Similarly pi4, pi5. This is just a name of the particular relevant partition. Now say I want to draw the Ferrers diagram corresponding to this one. The definition says there has to be ni dots or cells in the ith row. So in the first row, since there is only one element, one number here, so corresponding to this I will pick up the 4 dots, 1, 2, 3, 4. So these are the 4 dots and these dots have to be left aligned. So in this case there is only one part, so this becomes the Ferrers diagram. So let us write the Ferrers diagrams. This is the Ferrers diagrams that I am showing here. Now for the next partition pi2, there are 2 parts. So this means in this notation there are n1 and n2. And in ith row there will be ni dots. So in the first row there will be 3 dots and in the second dot there will be n2 dots. So we have to pick up from the definition, the first row have 3 dots. So this is 1, 2, 3. And the second row have only 1 dot. And we notice that these are left aligned. So this is the left alignment. So in this case, you can see that this is left aligned. Every dot starts from the left alignment. So this is what do we mean by left aligned. So we can just draw it here also. This is what we mean by left aligned. Now similarly in the next case, pi3, if I want to write the Ferrers diagram corresponding to this one, what will be pi3? This will be 2. So here it will be 2 dots in the first row. And then again in the second row also there will be 2 dots. Now for the next case, so let me to just take a bifurcation so that there is no confusion about the dots. So for the pi4, first row have 2 dots, the next have 1 dot, that's the value for n1, this is the value for n2, and then the value for n3. So we will have 1 more dot. And this is how we are making it as left aligned. Now for the last case, each n1, n2, n3, n4, their value is 1, 1. So first row have n1 dot, that is 1. Second row have n2 dots, that is 1. Third row have n3 dot, whose value is 1. And fourth row have 1 dot, this is this. So this becomes the left aligned. Now this is what do we mean by the Ferrers diagram corresponding to the partition. And for each relevant partition, there is a unique Ferrers diagram. Now I have also written that this is called as Young diagram in case we want to write this as a cell. So suppose if I want to write this in the in the form of a Young's diagram. So there is no much difference except then the way we represent. Now instead of these dots, what I'll do, I will use the cells. So it's like a square cell, and then you use 4 cells to represent the partition 4 in the first row. In the second case, we will first represent 3 cells, and then in the second row we will represent 1 because the next number is 1 and here it was 3. Then similarly in the next partition we will represent the cell 2 by 2. So this will be 2 by 2 cell. First row also have 2 cells and the second row also have 2 cells. Now in the next case again we will represent 2 cells followed by 1 more. So there will be 3 rows. Then similarly in the fourth case we will have 1 cell, then there will be 1 more cell, third cell and the fourth cell. So this is what do we mean by the Young's diagram. So this is just a representation. Somebody can also show it using the asterisk sign. So this is, instead of dot we may use asterisk signs. So we can write it like this one. So you can have 3 dots here and then you can have 1 more dot. So everything has to be left aligned. That is the one common thing in all the definition. And then we have 2 for the next partition, we have 2 asterisk signs. Then for this case we got 2 dots for the first case, then followed by 1 dot and 1 dot, and in this case everything is corresponding to 1. So this is how we represent a corresponding Ferrous diagram, Young's diagram, or the definitions written in terms of any symbol such as asterisk, where it fits into the definition of the Ferrous diagram. It's an array of dots or cells or asterisk, left justified dots with ni dots in the ith row. Now to understand what do we mean by conjugate of a partition, let me to consider a particular partition. Let P be the partition of a number 15. This be a partition of 15. So P is just a notation and I'm considering P, this 15 partition, as any one of the relevant partitions, 6 plus 3 plus 3 plus 2 plus 1. And let me to write down the Ferrous diagram corresponding to this one. So for this Ferrous diagram for P is, this is given as, now we know that it has to be left aligned. So we can have 1, 2, 3, 4, 5, 6. This is 6 dot. Then we have 3 dots and then we have 3 dots and then we got 2 and then we got 1. So we have this left aligned diagram, and to write this one we read horizontally. Basically this is how we read it, read horizontally to find the corresponding part. So if I read horizontally, this consists of 6 dots, then it consists of 3 dots, then third row consists of 3 dots, this consists of 2 dots, and the last consists of 1 dot. And these were actually the value for n1 plus n2 plus n3 plus n4 plus n5, and they were written in non-increasing order, and this fits into the definition as I've earlier defined. So what do I mean by conjugate? So conjugate of P. So this I'll explain in the definition from this example only. Conjugate of P means that read this diagram vertically. So now if I read the diagram, if I read the dots vertically, then we will see what partition do we get. Earlier I read it horizontally. Whenever we want to draw the Ferrous diagram, we have to keep it left aligned and read it horizontally, or you can say place the dots horizontally. But now if I read it vertically, so see how many dots are there in the first column. You can see, or you can simply say in the first the arrow that I'm showing, first column. Then read how many are there in the second column, how many are there in the third column, fourth column, fifth column and sixth column. So you can see how many dots are available in the column. So first column, either you can read it from top or bottom, doesn't matter. Now if I read it this way, if I read it vertically, then the first column consists of 1, 2, 3, 4, 5. So there are 5 dots in the first column, followed by the next column have 4 dots, followed by the next column have 3 dots, then we got 1 dot, then we got 1 dot, and then we got 1 dot. So this partition which we have got from the previous case by reading the graph vertically is what do we call it as a conjugate of that particular partition. And we also notice that this is a partition of 15 only. So this is a partition of 15 only. 5 plus 4, 9 plus 3, 12, 13, 14, 15. So this is again a partition of 15 only. and this is also called as transpose of the Ferrous diagram, and we may denote it as P dash or with any other notations. So let me to just write down P dash. This is the conjugate of P, and corresponding to this, if I want to draw the Ferrous diagram for the P dash, so Ferrous diagram for the P dash is exactly in the same way as I've drawn earlier. So we have 5 dots in the first row, then followed by 4 dots in the second one, third have 3 dots, then 1 dot, 1 dot, 1 dot. So again, once we have read the dots vertically, or we can say we read this as column and then make it as a row, then read the second column and make it as a second row, read the third column and make it as a third row, fourth, fifth, sixth column, they become respectively fourth, fifth and sixth row. So this is how, simply by changing rows into column, we get the conjugate of the Ferrous diagram. Now I define self-conjugate partition. If the Ferrous diagram of a partition P of n is same as the P dash, that is the conjugate of the partition, then that particular partition is called as a self-conjugate partition. So for this, let me to take an example. Let n is equal to 4. And in this case, when I take n is equal to 4, let's consider one of the partition for this. So consider P, which is equal to 2 plus 2. So this is one of the partition of 4, and if I now draw the Ferrous diagram corresponding to this one, we can see these are the dots. So this is the Ferrous diagram for the P. So for the P partition that I've considered. Now if I take its conjugate, so suppose if I now take the conjugate P dash, and if I now read this graph vertically, then also I notice that in first column have 2 dots and the second column also have a 2 dots. So obviously for this case also the Ferrous diagram will be same. So now we can say that this is the Ferrous diagram for P dash, and we notice that both of these these are same. So 2 plus 2 is a self-conjugate partition. Every partition is not a self-conjugate because they leads to a different partition. But in this case, this is a self-conjugate partition for n is equal to 4. We can take another example. Suppose if I take n is equal to 6, and in this case, say I consider a partition 3 plus 2 plus 1, 3 plus 2 plus 1. Let's say this is a partition P, and if I draw the Ferrous diagram corresponding to this one, this is 3 dots, 2 dots and 1 dot. And now if I consider P dash, so that is the P transpose, or that means the conjugate of P. And then for the conjugate of P, what I need to do, I need to read it vertically. And we see how many dots are in the first column. There are 3 dots. How many dots are there in the second column? There are 2. And then how many dots are there in the last column? That is 1. And this is exactly both are same. So we can say that the 3 plus 2 plus 1 is a self-conjugate. This is a self-conjugate partition of, this is a self-conjugate partition of 6. Now let's take another example. Say if I take n is equal to 5, and corresponding to this I consider a partition 3 plus 2. In this case, what will be the Ferrous diagram corresponding to this one? We need see that 1, 2, 3, and then we have 2 dots. And if I take its P transpose, so what will be the corresponding P transpose? For this, if I read it vertically, so this will lead to a partition 2 plus 2 plus 1. Now we notice that this is also a partition of 5, and earlier also it was a partition of 5, but they both are not same. These partitions are not same because the first one, n1 value is 3, and in this case n2 value is 2. Here n1 plus n2 plus n3, there are 3 parts and their value is different. So we can say that 3 plus 2, or you may say 2 plus 2 plus 1, these are not the self-conjugate partition. So self-conjugate partition are those partition whose, when we take the transpose, they lead to the same partition. These are not self-conjugate partitions of 5. So now we use the Ferrous diagram to prove this theorem, which is due to Euler, and this proof we call it as a combinatorial proof, since we are not using any analytic identity, although in my last videos I have used the generating functions to prove some of these such type of the identities, and so those are called analytic identities, but here I am going to use a Ferrous diagram. So let's look at the definition statement of this theorem. It says let k and n belongs to capital N with k less than or equal to n. Then the number of partition of n into k parts is equal to the number of partition of n into parts, the largest size of which is k. So on one side we consider the partition of n into k parts. So we consider the partitions of n into k parts. So here this means I can consider a particular partition of n, and let me to call this as a particular partition as pi, and this is a partition of n where we need to consider this into k parts. So by definition we already know that n1 is greater than or equal to n2 is greater than or equal to, we can write the parts in a non-increasing order. Now we notice that using the Ferrers diagram, so once we draw that Ferrers diagram, so what will we get? Ferrers diagram means the first row will have n1 dots. So let's say this is n1 dots that we are having, and the second row will have n2 dots. So now either the n2 is equal to n1 or it is n1 is strictly greater than n2. So without loss of generality we can just draw it dots here, or maybe you can just draw it till the last of the dot, doesn't matter. We just call this as a n2 dots, and we follow the similar pattern, and then we will have the kth row, because we know that there are k parts. So this means there will be k rows and the last will have k dots. So we have drawn the Ferrers diagram. Now what we do is we find its conjugate. So find conjugate of above partition, conjugate of above partition. And in this case my above partition is pi, so let me to call so we find pi dash, or sometime we can call this conjugate as pi c also. Pi dash stands for transpose, pi c stands for conjugate. So now when I find the conjugate of this, we notice here how many these are left lines, and as per the definition, every nk, since we are using the partition of a positive integer, these ni's are positive integer. That means every left aligned row will have at least one dot. So this may be, it is possible that the last part value is 1 and that one dot has to come in here. So this is not possible that the last row have not even a single dot. If this is the case, then we will consider this partition into k minus 1 part. When we say that nk has a value, this is kth dot, that means at least one dot must be present. So now when I count it as vertically, or when I consider its conjugate, this means the first it will create another partition of n, and in that case the first one, this is the largest part, and this value will be k because there are k dots. So since there are k dots, because k dots are available, these are available in first column. So when we read it vertically, we see there are k dots available in this one, plus then we can have the corresponding, so let me just call this as the value n1 dash, and then we have n2 dash plus n3 dash plus on. So we do not bother how many parts are there, because the identity says, now if I look at the identity, it says partition of n into k part is equal to the number of partition of n into certain parts. It is not mentioned into how many parts, but the condition is that the largest part size is of the type of k, or we can simply say the largest size is k. So this is a partition into some parts where the largest part is k. The only thing that we know when you read it vertically, that k is definitely greater than or equal to n2 dash. Now k is actually the value for my n1 dash, and this is greater than or equal to n3 dash, greater than or equal to nr dash. And hence by the simple explanation, or simply taking the conjugate of the Ferrers diagram, we see this identity holds true, and we also see the reverse implication, reverse also hold. So what I mean by reverse also hold means, if I consider a partition in which the largest part is k, and then I start reading vertically. So in this case, say we have largest part k. So suppose there are k dots. Now when I'm going to read it vertically, that means there will be k parts in that next conjugate of that. So the reverse holds from again taking the conjugate, and that's how we can prove this identity combinatorially. Now we see this from this quick example. Partition of 8 into 3 parts is equal to partition of 8 into parts where the largest size of which is 3. Because here I have considered 3 parts. This means the largest part size is 3. And this number, here this number is same as this number. This is why we are calling it as a partition identity. So now to see this, suppose I consider a partition of 8 into 3 parts, 6 plus 1 plus 1. This is 5 plus 2 plus 1. Here I consider 4 plus 3 plus 1. This is 4 plus 2 plus 2, and I consider 3 plus 3 plus 2. Now if I draw the Ferrous diagram corresponding to the first case, 6, 1, 1, we know that the partition will be 3 plus 1 plus 1 plus 1 plus 1. So one can draw the diagram and one can see it. We can see that quickly. 1, 2, 3, 4, 5, 6 dots. Then there are 1, 1 dot. Now if I read it vertically, 3, 1, 1, 1, 1, 1. And this is how I got this one. Now similarly, if I just follow the similar steps, 5 plus 2 plus 1 will correspond to 3 plus 2 plus 1 plus 1 plus 1. 4 plus 3 plus 1 will correspond to 3 plus 2 plus 2 plus 1. So this is how they will translate into one another. 4 plus 2 plus 2, for this also I show you 4 dots in the first row, 2 dots in the second row, 2 dots in the third row. Now read it vertically. And so this means 4 dots in the first, and 3 dots in the first one, and 3 dots here, and then 1 dot and 1 dot here. So in this case we will have 3 plus 3 plus 1 plus 1. And then for the last 3 plus 3 plus 2, we get the partition. In this case, it will be 3 plus 3 plus 2. In fact, this one we can call it as a self-conjugate also. So this partition is exactly turning into the same partition after the conjugate. So we can consider this as a self-conjugate partition. And to see the reverse implication, let's say I'm considering this partition. So draw the Ferrous diagram corresponding to this one, 3. Then there are 2 dots, then 1 dot, 1 dot, 1 dot. Now if I read it vertically, how many dots are there? We can see there are 5 dots. How many dots are there? There are 2 dots. And how many dots are there? There are 1 dot. So this is 5, 2, 1. This is the partition which is listed here, 5 plus 2 plus 1. Because the largest part is 3, so in the first row there will be 3 dots only. And these column will become the number of dots here. So this implication is reversible. And hence our identity follow, which is very evident from this particular example. Now consider this problem, and this is an application of the previous identity. One can see that using the previous identity that we have proved, we can solve this problem very quickly. Let AR denote the number of ways of distributing R identical objects into 3 identical boxes, such that no box is empty. Find the generating function for AR. So in my one of the previous video, I have solved this problem using the generating function R identical objects into N identical boxes. And there I have shown that this problem is equivalent to writing the number of partition of a positive integer n. So let's recall the whole. The link is added in the description, but quickly I want to recall it through this. Say for example, you have n is equal to 3. The relevant partition for 3 are 3, 2 plus 1, 1 plus 1 plus 1. So this means if you consider n is equal to 3, we need to consider distribution of the object into 3 identical boxes. And so for this one, we will consider 3 equivalent, or you can say identical boxes. So we consider 3 identical boxes. And if the part value is 1, this means all these 3 dots are to be assigned only in the one box, because there is only one part. So I will assign all the 3 dots in the corresponding to this 3. The value is 3. And so for this, I will put up all the 3 dots in one box only. Then for the next case, how will I assign? This is again into 3 parts. Everywhere this is into 3 parts. But now, if there are 2 parts, 2 and 1, the first part have the value 2 and the one part have the value 1. So 2 dots will go in one box, and the another n2's value. So this is the value for n1, this is the value for n2. n1 goes in one of the box and n2 goes in the another box. Then we have 1, 1, 1. So we'll put place 1, 1, 1. So there are 3 parts. This means every box have at least 1 dot. Now this is the problem of distributing R identical objects into N identical boxes when R and R are different. Now same thing, suppose here the condition it says that no box has to be empty. So this means these cases are not allowed, because we can see there are two boxes which is empty, here one box is empty. This means what our problem is saying? Our problem is saying that we want to consider a situation where every box contains at least one object. So this problem 1 plus 1 plus 1, this case, this is equivalent from the previous understanding. This is equivalent to write a partition with the largest part 3, with the largest part as 3, because when I take its Ferrous diagram, so if I take conjugate of this partition, so what I will get? First I will make the Ferrous diagram, which is one dot in the first row and one dot in the second row and one dot in the third row. So this is the pi partition, which is 1 plus 1 plus 1 of 3, and if I just read pi conjugate, I will get a partition which is 3. So this means this type of the things we are searching, in which there are 1 1 1 1 dots. So for example, if I consider a general case n is equal to n, this means I am writing a case 1 plus 1 plus 1 plus so on plus 1 up till n times. So when I consider up till n times, this means when I want to consider a partition of n into n identical boxes, so there are, let's say, n identical boxes, and each box has to at least one. So when I consider n identical boxes, every box consists of one dot. So this is what it means. Now if I consider this case, this is equivalent in solving where the largest part size is n. Largest part size is n. Okay, so this is what do I mean by the using of the previous theorem. Now we will create a generating function as per the part size. We know how to create the generating function once the part size is known. So for this one, now what I'll do, I'll create a generating function. So generating function, let me to first recall the generating function for the partition integers. Recall generating function for Pn. This is partitions of n. So we are considering all partition of n, and here the part size are not restricted. I'm just recalling the previous step. So we said that if the part size is 1, x to the power 1 may appear or it may not appear, x to the power 1 raised to power 1. Then x to the power 1 may appear twice and so on. This is the part size 1. For this particular portion, you need to watch my previous video first. Then the part size 2 can appear 0 time, part size 2 can appear 1 time, and so on. And this we will repeat for every other part. And this is how we written summation Pn x to the power n goes from 0 to infinity. And then simply using the GP, we said that this is the part size 1 for part size 2, for part size 3, and so on. And so the general function becomes product. So this symbols I am using it for product, I varying from 1 to infinity, 1 over 1 minus x to the power I. So generating function for distributing r identical objects into 3 identical boxes such that no box is empty is equivalent to finding the generating function for partition of n with largest part size as 3. And in this case again, we create the generating function corresponding to size 1, size 2 and size 3. Now we said that the largest part size is 3. So here what I am doing is I am taking x to the power 3 appearing 1 time, x to the power 3 appearing 2 time, and so on. So 3 can appear as many as number of time, but the size will not increase. So we will not consider x to the power 4 in the next terms and x to the power 5 because the largest size is 3. But 3 may repeat any number of time. And for this case, we say the size 1, it may appear or it may not appear. So x to the power 0 may appear, x to the power 1 may appear 0 time, plus x to the power 1 may appear 1 time, and so on. And x to the power 2 may appear 0 time, x to the power 2 may appear 1 time, and so on. And this becomes a generating function. So this will become x cube when I just simply take x to the power cube common from here. and in the denominator we will have 1 minus x, 1 minus x square, 1 minus x cube. And here we can consider an example for n is equal to 4. We said the largest part size is 3. So 3 can appear one time. You can see this 3 will multiply with 1 and 1. So this will be one of the partition 3 plus 1. Here the largest part size is 3. If I take n is equal to 5, I may consider a partition 3 plus 2. In this 1 is not repeating. If you take n is equal to c, we can consider 3 plus 2 plus 1 is a partition. Or 3 plus 3 is a partition, 3 repeating 2 times. And also we can continue finding any other larger number corresponding partition where the largest part size that we are using is 3. And hence this becomes the generating function for the required problem.